Okay, so in this video, I will show you how to correctly draw the shear and moment diagram from the result of your moment distribution method spreadsheet. So for example, we have this frame E with the loadings shown. Okay, you will notice you need to designate certain letters with the corresponding subscript for each joint in order to have a clear organization in your spreadsheet, in order to have a to retrieve the values later on. Okay, so for example, we have A naught or A0, A1 progressing to A2, A3, A4. On the next column, B naught, B1, B2, B3, B4, so on and so forth until you have H naught, H1 to the last column. And using the spreadsheet as shown, or although it's in a PDF format right now, my student uses those subscript or designation to organize his calculation like this. Okay, so for example, A naught going to A1, the stiffness is 1.693 of that column. This by the way, that this should be distribution factor 0 because it's fixed end support. Okay, and then you have a corresponding fixed end moment and the balancing and the carryover moment at 10 iterations. Okay, and then when you sum this up, you will come up with a moment of 6.02 here, while A1 going to A naught or downwards, it's 12.03. Okay, so that's what you get in the spreadsheet. Now you need to plot this in the FBD or free body diagram. Okay, so 6.02, 12.03. So for our convention, you need to show the arrow, this one. So this is 6.02, while A1 going to A naught is 12.03. That is positive. Okay, 12.03. Okay. So I have now an FBD or an incomplete FBD of a column. So when you have this moment going clockwise, so to make this stable or in equilibrium, you need to have a corresponding couple of forces to resist that that clockwise rotation. So to compute that, by the way, the height is what? What's our height here? 2.8. Okay, that is the height is 2.8. 2.8. 2.8. Okay. Okay. So how do we compute the force here? Simply, the reaction is just 12.03 plus 6.02, okay, divided by the height, 2.8. What do we get? So we will get 12.03 plus 6.02 divided 2.8 is 6.45. So 6.45. Therefore, our reaction there is 6.45 kilonewton. 6.45 kilonewton. Okay. So if you wanted to draw the shear diagram of that, okay, so this is going right, therefore this is going right, and this is upward. This by the way, this is negative area. Okay, so this is the shear diagram. Okay, how about moment? So it's going to the left, so it's going to the left. Okay, now to be consistent, take note this is 6.02, and the value of this shear is 6.45. Okay, I'll change this one. Now, to be consistent, 6.02, as we said, as our principle or concept in shear and moment diagram, this value 6.02 will be subtracted by the area of this one because this is negative. Okay, so the value, but wait, let's observe this moment here. It's going to the right. Therefore, we expect the moment is here. Okay, with a value of 12.03. Okay, and then since this is a 0 degree shape or slope, we have first degree slope like this. Okay, it's first degree. So let's check the consistency. So the value of, so this is the moment B, which is 12.03, is equal to 6.02 minus the area of this one, 6.45 times 2.8. So answer good. What's the answer? 6.02, 6.45 times 2.8. So there you go. You have negative 12.04. So there's a discrepancy of about 0.01. Okay. So this is a negative area and this is a positive area. Okay. So you should come up with this uh, uh, shape or diagram for shear and moment. So let's see. The shear diagram is this. So that's it. So that is 6.68. Okay, so he got 6.45. Okay, I got 6.45 in discrepancy. So this is a negative area about the moment. There, 6.24 or 12.4. They're almost the same. Okay, there's just a discrepancy. Okay, so that's it. So it's consistent. Okay, that means on this procedure, we are saying that I am following this convention, similar to how you get the fixed end moment. Okay. For example, I have this uniformly distributed load. How do we draw shear and moment diagram there? And this is your shear, okay, and this is your diagram, right? That means this is a positive. Okay, this is this. Okay, and the elastic curve here is something like this. Oops. Something like that. And this is tension. This is compression. This is tension. This is compression. This is compression, this is tension. Okay, that means on the left, the negative moment here, which is negative WL squared over 12. On the right, that is positive WL squared over 12. So negative going down, okay, negative area, okay. Then this one is going up, so this is so the shear is going up on the left side, okay. And this negative moment will cause compression on the bottom fiber, okay. So that's it. This is the bottom fiber of your section. The negative moment from the left will cause a uh, compressive stress on the bottom fiber. Okay, so that's very easy. Now, when you go to column, it's a different story. Therefore, in the beam, we are following this convention left to the right. And for column, we should follow this convention of down going up. Okay, that means left in the beam is correspondent to bottom or down part, or the bottom part of the column. Okay, so this one is simply the left portion of your beam, and this one is simply the right portion of your beam. Therefore, your convention here should follow the convention on the left portion of your beam. Okay, like this one. So we said this bottom will follow the left convention, sign convention of your beam. This is going down. Therefore, your shear diagram should go downward. Okay, this is going right, sorry. This is going right, therefore it's going downward. Okay, simply when you rotate this into like a beam, okay, this going to the right will simply means going downward. Okay, that's it. So negative area for the shear. Like here, it's going up, so it's a positive area on the shear. Okay, on the shear. How about here? This one is going down. Okay, so this is negative, but this one is going up, so this is a positive. Okay, positive. Therefore, this should therefore in your column, that means it's going to the left. Okay, that is positive. Okay, going down, negative area. Going up, positive area. Okay, so that's it. Going up, positive area. Going down, so this is analogous to the or correspondent to the right portion of your beam. This is the right portion of your beam. Going down, negative area. Going down, negative area. Okay, so that I think you should follow that procedure or sign convention in drawing the correct shear and moment diagram. So in order to be consistent, okay, let's try with the beam here. So MDM or loading frame E. So here 24.403. So our beam corresponds to A1B1. Okay, A1B1. Here A1 B1. Okay, let's see the result. A1 B1 A1 B1, this one. So A1 B1, he got negative 30.75. Okay, A1 B1 negative 30.75. So negative, that means going down. Okay, negative 30.75. How about B1 going A1? B1 going A1. B1 going A1. Where's that? This one. So B1 going A1, he got 33.44. Positive. Positive is this. 33.44. Okay. Then let's incorporate the loading, 24.403. So you should incorporate the loading here. 24, arrow here, 0.403. 403. So to be in equilibrium, you need forces. Okay. Okay. So let's see what's the direction. So let's say this is A1, B1. So summation, what's that? Summation moment A1 is equal to, this one is negative 30.75. So that is equal to, okay. So in order to get RB, so I'm getting force at RB. Okay. So that is 24.403 times, what's the distance? 4 times 4 times 4. So that is going clockwise. So it will be held by 33.44 plus 33.44. Okay. So who will resist that? They will counteract. They will be resisted by RB. Okay. Minus RB times 4. Okay. So one equation, one unknown. We will get RB is equal to what? Okay. So negative 30.75 minus 24.403 times 4 minus 33.44. Divided by 4, I'm getting 40.45. So I'm getting 40.45. Okay, so that means this is going up 40.45, 40.45. So by equilibrium, we will need 24.403, the vertical force downward, resisted by times 4, resisted by 40.45. So he needs help from RA of 57.162. By summation force vertical, you will get 57.162. Okay, so that's it. You now have shear diagram. It's our convention. Oops, where's this convention? Okay, going up, positive. Okay, going up, positive. So going up, positive. So this is 57 0.162, 0 degree, first degree. Okay, so this is definitely 40.45. Okay, so this is your shear diagram. Shear diagram. About the moment. For the moment diagram, I have this. Okay, so for our convention, to the left, on the left portion, this is negative, going to the negative area, going down. Okay, going down, negative, going down. Okay, so that is negative 30.75. Okay, so you just need to compute x here. Definitely somewhere here. So first degree, this becomes second degree. Okay, and another second degree. And definitely you will get moment B of 33.44. 33.44. Okay, so let's see. Moment diagram. Okay, frame E. Okay, where's that? Where's the FBD? FBD. Okay. Okay, so 33.44. Okay, and then 30.8, 30.8, 33.44, 33.44. Okay, okay, 24.403. Hmm, I think something's wrong here. Negative 44. Ah, okay, this should be positive. Okay, okay. Because this is positive because 24.403 is already resisting this 30.75. Okay, so they should have the same sign here. Okay, because this is going counterclockwise and this is going, sorry, this is going counterclockwise, this is going clockwise. So that means 30.75 minus 24.403 times 4 minus 33.44 divide 4. Uh-huh. Mhm. 24.403 minus 24.403 plus 4 minus 33.44. Okay, divided by 4. And I'm getting 25. Oh, shit. Ah, okay. Wala akong lever arm. So I don't have lever arm here, which is 2. Okay. 0.44 divided by 4. Okay, so this should be 49.5 or 48. 48. Okay, I forgot the lever arm here. So this one is 49.48. Okay, this one, where's the eraser? Eraser. Okay. Okay, so this is 49.48, and this one here is 48.13. Okay, so consistent. Okay, this is the FBD. Okay, and let's see the shear diagram. Okay, that one. It's the shear diagram, consistent with this, and the moment diagram. That one. Okay, so that's it.